Hello, I am Rupak Mukherjee. I am a postdoc at Princeton Plasma Physics Laboratory. I primarily work in the Jekyll group with a focus on gyrokinetic simulation for tokamaks. This work has been performed with Noah Mandel, Mana Francisquez, Tess Bernard, Amar Hakim, Greg Hammett, and the Jekyll team. Here we have performed simulation of Aztec's upgrade scrape-off layer plasma turbulence with full F gyrokinetic continuum electromagnetic gyrokinetic model. Basically. What are we simulating here? So we have simulated the scrape-off layer of a tokamak, and the simulation regime that we are trying to capture here is the all bad curvature regime, primarily in the around the outboard midplane of a tokamak. So here, if you can see the red toroidal or helicotoroidal region, this is the simulation domain, and we straighten our simulation domain like this. So in the next slides that I'm going to show here is primarily the simulation, or the movies will be shown in this kind of geometry, where the z-axis is the magnetic field line following direction, and x and y. X is the radially outward direction in the SOL region, and y is the binormal direction. What we have simulating, and how are we simulating this tokamak scrape-off layer? So we are using 3x2v electromagnetic gyrokinetic equations on magnetic field line following coordinates. So here you can see the thin toroidal or helicotoroidally wrapped line. This is the magnetic field around that is wrapped in the SOL region of the flux surfaces. And this thick red blob that you can see extended along the magnetic field lines. So these blobs, they get shear off from the separatrix region in this picture that you see here. This is the helical direction, and this is the z-axis. There is a magnetic field line following direction, the radial direction. So they shear off from the separatrix region and propagate in the far SOL or far sol region. What are included in our simulation? So we are simulating the evolution of the full plasma distribution function. That's why F is the distribution function of the plasma. It's a function of three space and two velocities. The standard 3x2v model, gyrokinetic model. We are doing this expensive and very exhaustive simulation because we need to capture the turbulence better. It's very highly turbulent, and we need to do some first principle simulation, direct numerical simulation to capture this. And we have to be, numerically our accuracy need to be very high. So this is important. Our simulation is electromagnetic such that it can actually capture the field line bending effects. So our algorithm does not suffer from any ampere cancellation. More details can be found in Noah Mandel's JPP paper in 2020. We are simulating the SOL plasma with discontinuous Galerkin algorithm for better accuracy and the helical magnetic field. So I'm using this cartoon for helical magnetic field everywhere. The helical magnetic field actually helps to reduce the simulation cost by a significant factor, because as I showed in the previous slide, the plasma blobs, that spontaneously get generated in the around the separatrix region because of the shearing off. They are primarily the structure of the blobs are primarily field line following, so that's fine. We are using Leonard-Bernstein collision operator with intra as well as interspecies collisions. So we have ions and electrons both species, and they collide. More details about the Leonard-Bernstein collision operator can be found in Mana Francisquez paper in Nuclear Fusion 2020. And we are using realistic deuterium mass ratio. So with this, all these hands, we set up our simulation for ASDEX parameter, ASDEX tokamaks parameter, ASDEX upgrade shot number 33292 and 33341. The details of the shots and experimental measurements, analysis of data, and everything has been documented very nicely in Daniel Carollo's nuclear fusion paper in 2017. Here in our simulation, we specify the initial ion and electron density and initial density equal to 0. So at the beginning of the simulation, electron and ion temperature at the separatrix location only. So effectively, it's like providing the information of initial ion and electron density and temperature from this reference, from this experimental reference, and providing the information only at one location in the simulation geometry. And we let the simulation evolve, and the profiles, radially outward profiles, they get self-generated with time. And then we compare these self-consistently evolved radial profiles with our simulation and then compare them with the experimental data. And the density and temperature profiles, those profiles we measure in some statistically steady state of our simulation. And as I said, the density blobs, they are typically elongated along the magnetic field line following direction of the z-axis. And this helps us to reduce our simulation cost. So this is the view in the z equal to 0 plane at the same frame rate, identical things. And they shear off from this separatrix region and propagate in the radially outward direction. And this is how they enhance the turbulence in the scrape-off layer region, thereby reduce the diverter heat load. So we finally measure the diverter heat load at a statistically steady region. And this is to note that these are electromagnetic global simulations. So these field lines that you see, these white thin field lines, they dance in 3D. So that's a beautiful thing we capture. And here we provide the comparison of our Jekyll simulation data with the experimental results measured. So both for electron and ion density, electron and ion temperature. As I said, these numbers are taken from experiments. Only this one number from here and one number from here at the separatrix location for both for density and temperature for electron and ion both species. And then these profiles are self-generated species. And what is interesting to note is, even though in our simulation we start with roughly the same electron ion temperature, the profiles of the electron ion the temperature, they evolve, and you can see the ion temperature is more than double of the electron temperature. This is something we find in the experiments as well. So it's really self-consistently evolved profile. And further, we try to measure the density blobs. The density blobs are known to be the primary carrier of heat. So we need to know the dynamics, their velocity, their correlation functions, etc. So as I mentioned, they typically shear off from the separatrix region, which is this red dotted line, and they propagate in the far SL region with the E cross B velocity. However, the background turbulent plasma, as well as the parallel connection length, whether they are sheath limited or whether they are like detached, whether they are inertial in the inertial range or not. So depending on this different physical scenario, their velocity and also the rate of propagation in the far SL region, also the number of the blobs and all these things changes. So we try to measure from our first principle simulation and then compare the blob dynamics with the experimental one. So here we provide the data from the Jekyll simulation, and this is for the same shots, we may compare them with the ASDEX upgrade measurement. What you can see is this is mostly in simulation we are bounded within the sheath limited regime. So where we have the 0 to 50 roughly. So here also we have like 10 to 50. They're not exactly one-on-one, of course, but roughly they're close. The perpendicular velocity and the blob size, etc. Also, the filament packing fraction, if you look for the low collisionality cases, lambda less than 0.5, that means this inverted red triangles. So the packing fractions also are close. We have also measured the autocorrelation functions and other stuff. So they also appear close. For the low collisionality cases, high collisionality runs are expensive and they take more time. Finally, we also measure the parallel ion heat flux normal to the lower diameter fields. Our numerical measurements are found to be pretty close to the experimental parameters, experimental measurements that has been reported earlier. Again, we'll have to consider only the low collisionality cases, number-wise. Roughly the profiles and the magnitude-wise, they are close. In summary, we have performed a full F electromagnetic gyrokinetic simulation. We call this EMGK simulation using the Jekyll simulation computational plasma architecture. And this captures the essential features of the S-well turbulence for the parameters which are experimental parameters that are close to Aztec subgrid measurements or Aztec subgrid shots. One interesting thing is, even though we start with a similar temperature profile of electron and ion temperatures, to similar temperature at value at the separatrix region, the self-generated profiles, they show that the final ion temperature that is more than double of the electron temperature, and this is something that we find from the experiment also. We measured the density blobs, and we found we track the density blobs with time, identify the blobs, and then we track it, measure its velocity and all other statistical quantities. And we have found that roughly the quantities are close to the Aztec subgrid measurements. More realistic features, for example, shear in the magnetic field, neutrals, or like even better collision models, specifically the things that I'm working on now. We explore high density, high collisionality plasmas. The shear and the neutrals have been implemented, but the collision modules that we are working on. And once they are implemented, I will explore the Aztec subgrid like parameters and then try to capture the other regimes also. I acknowledge, of course, the Jekyll team and Gregor, Thomas, Vladimir, Dominic, Andreas, and Frank Yanko from IPP Garkin. Thank you very much for your kind attention.